now I think it's time to start. So the first talk, and we are very happy that she kindly agreed to give some time to 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 share her new, I mean, some of her results.
Thank you, Camille, for the invitation. I'm very
And
glad that I can contribute. Thank you.
so yeah, so it's Janet Anders, and I think you can start sharing your
Sharing the screen, right?
screen and
Can you see the slide?
yes.
Okay. Mm-hmm.
And yeah, so yeah, I will be sharing this first session. So I guess most of you are already a bit familiar with the Zoom. But so if you have any question, please you can use the Q&A button so to ask a question, or you can also raise your hand and we will give you the possibility to switch on your microphone and ask a question. Okay, so Janet, please, you can start whenever you are ready.
Yeah, thank you very much, Camille. I hope you can hear me okay and see the slides
Yes.
fine. Cool. Yeah, thanks very much for organizing the workshop. I know it's a really tough time, and getting it all moved online is a major operation. So well done for getting it all sorted and organizing such a nice program. We're looking forward to the week. And so I'm going to give the first talk, and because it's the first talk and it's also a new workshop series, you are thinking of maybe continuing in the coming years. I thought I start with some historical background first, of how did we actually get here? Why do we do quantum thermodynamics these days? Before I start talking about some work that my group has done, so I'll talk about this work from coherences. That's something that many of you will have seen who are old to the field, but it's probably new to some newcomers. And I'll also extend then to what happens if one wants to extract work from quantum coherences, but one also has irreversibility occurring in the process. And I'll also talk about how this coherence work is affected if you have side information, which is correlations to another auxiliary system. And all of these things are quite interesting also in the context that Chris Jaginski talked about in the Quantum Thermodynamics conference, where he actually talked about a classical analogon of some of those quantum coherence work extraction schemes. So we'll get in the end. At the end, I will talk a little bit about the strong coupling corrections thing. This is a whole new topic, so I will only touch on that before we end with this talk. Okay, yeah, and if you have any questions, I can certainly take a couple of questions during the talk, and then otherwise at the end of the talk, please do interrupt, because it makes the whole thing much more lively and much more interesting rather than just me talking all the time. Right, cool. So I'll start with the historical background. So let's go back to the 1800s, where thermodynamics was invented. You're all familiar with it, right? One of the key things about thermodynamics is that it has these laws of thermodynamics, the first law, the second law, and one of the key quantities here really is the entropy. So the entropy was introduced then, and it is the thermodynamic entropy. And as you know, the entropy has to be bigger than the exchange heat, and I'm not going to go into the details of this, but this is the first time the concept of entropy has turned up. And as you know, since then, we have the development of statistical physics that gives us a microscopic, actually the underlying physics that gives us macroscopic thermodynamics. And really that was the state of the art for many years. So this is the 1880s or so when statistical physics started. Now, going forwards, the next time entropy was really discussed in a completely different context was in the context of information theory. So you probably know that Shannon came up with another concept of entropy, and that's the entropy of information. And so this builds the whole ground for what we have today, right? Computers that manipulate information. And yeah, well, that was in the 50s. Now, of course, people were asking, okay, so now we have two kinds of entropy, the thermodynamic entropy that obeys the second law, and this information entropy that Shannon talks about, right? So how are they related? That was a big question at the time. And this is where Landauer came in. And he said, well, actually, information is physical in the sense that when you encode information, like in computers or so, there is a physical host of the information, something that carries the information, and this physical host will obey the laws of of physics and including thermodynamics, and that means that you cannot manipulate information without also obeying the laws of thermodynamics. And in particular, when you talk about information erasure, he showed that information erasure will cause heat dissipation. So information erasure in his language here, I'll just move it out of the set. So information erasure is maybe slightly odd for those of you who are not familiar with Shannon's information. Information is the uncertainty, okay? Information is the uncertainty of not knowing whether you have a 0 state or 1 state. So this here on the left is 1 bit of information. You do not know whether it's 0 or 1. And the erasure of information actually corresponds to moving that state to the 0 state. This is complete certainty. You have for sure 0. So this is actually erasure of information. And what Landauer showed is that this type of process going from row to 0 must be accompanied by a generation of heat, which is at least kBT log 2. And the T here comes from this erasure process being done in an environment at temperature T. So this is where the T comes from. And so the main thing that Landauer did is really connecting the two worlds, the world of thermodynamics with the world of information. And that was basically the state of the arts in the 60s. Now, what this has led to is actually quantum information theory. So Landauer's idea that information is physical also implied that if you replace a classical carrier of information with a quantum carrier of information, then surely the information will have to obey the laws of quantum mechanics. And that is the whole point of quantum information theory. And as you know, in quantum information theory, we have two types of properties, quantum superpositions and also quantum correlations, that are key to many of the quantum advantages that we see, for example, in quantum computing and in secure quantum key distribution. So yeah, basically Landauer's idea brought us all the way to quantum information theory, which started, I believe, in the 80s. Now, if you want to know more about this, maybe you want to go to this meeting that comes up on Wednesday. So this is in Krakow, and it is a memorial lecture for Roman Ingarden, and he also worked on a paper that's called Quantum Information Theory in '76. And Charles Bennett, who was one of the main people really who started developing quantum information theory, will give a talk in this memorial session here. But back to our story. So quantum information theory started in the 80s. But since then, also statistical physics has basically had an update. So we now have something called stochastic thermodynamics, which is a little bit new and different from just the usual statistical physics. In particular, it talks about even things like work, here W, as a stochastic quantity, not just one work, but actually there's many works, and you have fluctuation in the work, and you have averages over the work, you have work distributions and all that. So you have this Dzerzhinsky equality that some of you will be familiar with. Okay, now this is the scenario in which we find ourselves. This is just a slide to explain stochastic thermodynamics. I think I skipped this. So where we find ourselves is that quantum thermodynamics really has popped up here, and it's basically sitting somewhere between this thermodynamics, stochastic thermodynamics side and the information theory, quantum information theory side. And the community also consists of people with backgrounds from those directions. And then obviously the first ideas of doing quantum thermodynamics in this modern time were, okay, let's try and take stochastic thermodynamics and develop quantum fluctuation relations. So take this classical theory and make it quantum. And this was done. So I'm not going to go through the details. So there is something called the quantum Jarzynski equality, and you can look at these papers up here. And there's a whole raft of stuff that you have to go through. But the final line of it all is that you get a Jarzynski relation in the quantum case as well. But the quantum Jarzynski relation is exactly the same as the classical one. So actually, in some sense, it's maybe a little bit disappointing because there's no difference. So it seems nice, but not so exciting. So another way of approaching quantum thermodynamics came from quantum information theory, and this is what we call resource theory. So this is the idea that you can manipulate states under certain classes of operations. So here's a quick slide on resource theory. So I'm not going to go through this unless someone asks me. Very briefly, it's about a system rho, starting in a state rho, and then coupled, well, there's also a bath and also a work storage system. You have some unitary, and what you want to do is you want to lift your weight from the ground state to the excited state. And the question is how much work is needed, and this is called the single shot scenario here. And well, okay, so there's basically there's lots more to say about this, but the end result of it all is that actually what is described in these papers here from Horowitz and Oppenheim and also Arberg is a situation where still we have no quantum effect. It's actually a finite size effect. It also occurs in a classical setting. It comes from having a small set of individual independent copies, but there are only a few of them, not many. So it's not quantum in the sense of we have no non-diagonal elements. So rho is actually diagonal in energy. And also the unitary that one applies here commutes with the global Hamiltonian. So it doesn't generate something quantum in that sense. So in other words, these results are also not very quantum. They are small scale, but not quantum. Okay, so that was the state of the art in around 2015. So neither of those approaches had identified a quantum feature. And this is where what comes in, what I'm going to talk about now. So this is basically work we did in 2015. So let's recall Landau's thermodynamic analysis was actually a classical information process. It was the erasure of a bit of information. I've used the quantum notation, but it is just a bit of information being erased to the zero state. And the idea was, let's consider actually a quantum information process, something that is really generally quantum. And what we looked at was projections of quantum states, or also called unselective measurement. So for a given observable, for example, a Hamiltonian with a basis Ek here and some energy eigenvalues Ek, we are wanting to consider projections, which are state transfers, where we have an initial state rho, and we want to move it to the state eta, where eta is defined as, well, it's basically the probabilities pk are the chance that when you measure the energy on the state rho, you get the probability pk times the projector on the state ek. So in other words, this final quantum state is the original state rho, but measured in the energy basis, and then you forget the measurement outcomes. In that sense, it's an unselective measurement, okay? So again, we want to look at the state transfer from rho to eta, and just like Landau, we want to say what are the heat and work exchanges in this process. So before I get there, let me just give you an example. So if you have an equal superposition of two energetic states like this, psi is E0 plus E1, if you write it in density matrix form, you will get a state like that. And the projection we're talking about here is you basically remove all the off-diagonal elements because you do a measurement in the energy basis, and so the off-diagonals will vanish, and so the final state is this form. So we're interested in this type of process, and we want to now analyze it thermodynamically. So first let me state. Yes.
So there, Jeanette, there's one question, which is, so why projections are called unselective measurements, and what is selective, unselective measurements?
So let me start with unselective measurement. So this expression here is what is called an unselective measurement, or well, the measurement itself I haven't described on this slide. But when you take the state rho and you make a measurement in the energy basis, you will get one click in one possible outcome of the energy. For example, k equals 1, okay? Then you have a state that is actually the E1 state. So you get this projector with E1. That would be one possible outcome. Now you repeat this type of experiment many times and you get different outcomes. Sometimes you get 2, sometimes you get 3, and so on. You evaluate the probability for them, but the probability is simply this. It would be a selective measurement if you just stop there. So you have a probability for a certain outcome and you have the final state after this outcome. But an unselective measurement is when you forget what outcome you had. So you take all your qubits or states rho that you have measured, and you basically put them back into a box, forgetting about what state you had found. And that means that you actually make a mixture of these states. So you mix them again with the probability pk that you had a particular outcome. I'm not sure this was easy to understand, but basically unselective means you do average again over the probabilities pk at the end. Why we call it projection? We call it projection, maybe I get to this in a minute, because of a geometrical argument. It's just a different name that we introduced for it. So what we want to focus is the state transfer from rho to eta. So actually, how exactly we got there is something that we're going to discuss in a minute. So the state transfer is what we call a projection from rho to eta. So let me first tell you then that what one can show relatively simply on thermodynamics arguments really is that the optimal implementation, it tells you that you should be able to extract a maximal amount of work that is given by this difference of entropies, and these are von Neumann entropies, okay? So the difference here is that is the von Neumann entropy of the initial state, this is the von Neumann entropy of the final state, and it's multiplied by kBT. Again, that is the temperature of the environment in which this process is performed. And what is noteworthy is that these two entropies are different from each other if the initial state had coherences. So if indeed we had coherences in the energy basis, this entropy difference will be bigger than 0. And that means we can extract work from coherences. So we remove the coherences, and by doing so, we can extract work. Okay, so this is just a mathematical argument. Yes, Camille?
Yeah, sorry, one other question, which maybe is related to what you just said. Is related to what you just said. It's so must the unselective measurement be in energy basis specifically in order to erase information? Is this to ensure final state is stationary in time?
No, you can also, so that's a good point. So I've given here, for example, the Hamiltonian. You can also do it for different bases, so not the energy bases. When you do that, you get into the work expression here. You also get a term that comes from energy change. Okay, so I'm discussing the simplest case here, where the basis is the energy basis, but you can extend it to other bases. And no, it has nothing to do yet with stationarity. We don't touch on that. So this is not, this is the dynamic aspect of it is not crucial in this part. Let me move on. I think maybe some things will become a bit more clear when I move on. So firstly, we've introduced the projection, which is rho to eta. That's simply the definition of what we want to do. And what I've told you is that this is the optimum work one can extract in such a process. But now you may be confused because you say, well, okay, the desired state transfer was rho to eta, but isn't that exactly what decoherence does? Decoherence removes coherences in the energy basis. Isn't that what happens? So indeed, this state transfer is achieved by letting a system interact with an environment in an uncontrolled fashion for a long enough time. And of course, there's no work extracted in this process. Nothing extracts work. If you just let the system sit in a bath and it removes the coherences, no work is extracted. But that's okay. It's simply a non-optimal process. So all we find is that going back, this is the maximum work you can extract. It doesn't mean that every process from rho to eta will extract that work. It's a bit like you have a bucket that you've lifted all the way and it can do work, but instead of making it use this work to lift something else, you just drop it. So you extract no work from that potential of extracting work, okay? So decoherence is not a counterexample. It falls into the same class of possible transfers. But what we're of course interested in is how do you do this transfer optimally? So how do you do it such that you do get the maximum work out? Okay, so the optimal work extraction scheme is described here, and it is confusing for most people when they see it the first time. So if you're confused, please let's discuss it at the end of the talk, because otherwise I know that we can talk half an hour just about this. So the qubit example is shown here. So the ground state here is on the North Pole. So in our energy base, this is the plus minus, is the North Pole, South Pole direction here. And we have an initial state with a Bloch vector that points here. So this Bloch vector shows that we have coherence. And what we want to do is we want to do a projection process. And now the word projection starts to make more sense, because actually the final state that we are aiming for is this eta state, which has a Bloch vector, which is shown in red here. And so it obviously is along the energy axis. And what you can see is it is the projection of the black vector onto the red vector here. So this is why we call it projection, okay? So geometrically, we want to go from here to there. But the question is, how do you do it? And what you can do is you can, of course, you can manipulate the energy and the state of the qubit by changing the magnetic field of a spin. So I'm thinking of a spin that gives the energy to the spin. So we start with a state rho, that's this state, and with some field B0, that's over here. So that tells us what the splitting is in the north-south pole direction. Now we apply another B field to perform a unitary rotation of the state into the energy basis. So we need a B field that points in a different direction, in an X direction if you want. And what it should do is it should rotate our spin up there so that the coherences are gone. You can then also adjust the B field in such a way that this state that we've achieved here now is actually a thermal state with respect to the environment in which this spin is going to sit in a minute, okay? I know this is confusing, but you can adjust the B field always such that probabilities of your spin that we already have here, which are certain probabilities are given here, they are thermal for a given temperature if you adjust the B field correctly. Okay, there will always be a B field such that this state is actually thermal with respect to the bath's temperature. Okay, that was the second step. The third step now is simply to couple the system to the bath. So I'm thinking of the spin actually sitting in an environment. So far, I've done everything very fast so that the spin doesn't actually talk to the environment. But now in the third step, I do nothing, and the spin will couple to the environment, and nothing happens because it was already thermal. So it keeps on being thermal. Now the fourth step is to thermodynamically slow, so quasi-static, in other words, vary the field. So by changing the magnetic field very, very slowly, we can keep the spin always in a thermal state, but the thermal state itself changes very slowly, and we can pull the thermal state to be such that we have the eta state. So it's possible to find the B in such a way, this is this here, the B is adjusted such that this state is the final state. So we've achieved our final state that we want, but now we have a different B field than we had initially. So that was not really intended. So we have to return back our field to the initial field, so that all that has happened is that the spin has changed, but the external situation is the same. The bath is the same, the external field is the same. So this final adjustment of the field is just to return to the initial field. Okay. Now that we've got these 5 steps, we can analyze how much heat and work was exchanged in this process. Before we do that, let me just comment that so far I'm talking about an optimal process, so I'm not allowing any irreversibility. So I'm not allowing that there's something that doesn't match perfectly. Everything is wonderful in this scenario, but of course, if irreversibility were included, it would occur when the system is not in a thermal state before contact with the bath. If it actually still had some, classically speaking, some non-equilibrium distribution, not the Boltzmann distribution, of course it would lose this non-equilibriumness when you couple it to the bath, and this would lead to irreversibility, and it will affect the work in the heat exchanged. But for now, let's just go with the optimal case. So in process 1 and 2, the process is very fast, the system is isolated, no coupling to the environment, and so the work is the entire energy change that the system experiences in these 2 steps. In the 4th step, we have a quasi-static process, so the work is equal to the free energy change. This is just standard thermodynamics arguments. And in the final step, again, the process is isolated and the work is energy change. I don't expect you to understand all of these things in detail. I just want to outline how it works. And what you get in the end, when you sum all of this up, is you get exactly what I told you. You get the maximum work that I told you that you can extract. So in other words, what we've outlined on the right is an optimal process of extracting the maximum amount of work from the state rho when projecting it into the state eta. So just to say this one more time, a quantum system that has coherences in the energy basis here can be brought into a state where these coherences have been removed, and we've shown how to do this by realizable thermodynamic steps. No change of the energy expectation value has occurred. So this is this picture here of the projection. So the actual projection, which tells us also the value of energy, this is the same projection in the energy basis. So no change of energy has occurred. But the quantum entropy of the state has been modified. So the entropies of these 2 states are different, and the work is really extracted from this entropic change. So compared it to the classical case, so in the classical case, you have energy populations that are non-thermal. I already talked about this. So when you have a non-thermal distribution, classically, you can extract work from it by letting it push against the piston and thermalizing at the same time, extracting work from that. But what we've shown here is that you can also extract work from energetic superpositions, okay? Even though there's no energy change, but there's an entropic change. So in what I described, the extracted work is actually done on the magnetic field. So it's not so easy to measure it, but one can think about how to convert it into an actual work storage system where you can actually see that the work has come out. And just to say that the optimal protocol that I described it for a qubit, but the idea is exactly the same for any discrete system with dimension 2 or higher. So you can always think of such a protocol as what we described. Okay, so back to our big picture. So we've talked about where quantum thermodynamics sort of started or what ideas have been done. We also talked about quantum information theory and identified that quantum superpositions and correlations are really key to quantum information theory. So now we understand how quantum superpositions, or in other words, coherences, are somewhat important for quantum thermodynamics. And we showed that actually drawing work is possible when you project, so when you remove these coherences. There's also something about quantum correlations. We'll talk about this in a minute, a little bit in a different context. So quantum correlations, you can use them to draw work when erasing. I'm not going to explain this. This goes back to a paper by Del Rio and so on. I will not fully explain it, but I will mention it in a minute. Okay, so basically the 2 quantum things that are important in quantum information theory, we have now a picture of how they are important in quantum thermodynamics. Camille, I just got a warning that my internet connection is unstable. You can still see me, yeah?
Yes.
Yes, good. Okay.
Yes.
Okay, I shall continue. So So the quantum coherence has been discussed a lot since then, since this 2015 paper. So there's, for example, one paper that Marty will talk about this Thursday in this workshop here, is also about quantum coherences and how they affect the work fluctuation dissipation relation. So I'm not going to explain this one for sure, but please do go and see Marty's talk, which basically goes also on about how coherences are important for quantum thermodynamics. Okay, so I want to now very briefly discuss the case that what happens when we have irreversibility of the classical or the quantum kind. As we already said, this irreversibility can occur when the system is not in a summer state before contact with the bath. So in other words, we do this process, but instead of doing the perfect unitary, we might end up doing a slightly too short unitary. And we end up with a state here that still has some coherences left. And in fact, is also sort of classically non-thermal in some way. So roughly speaking, the coherence is sort of the distance of this blue star from the energy axis. And the non-thermality is sort of the other axis of how far away it is from this point from the thermostat that was intended. And so these two things are going to cause irreversibility. So specifically for this non-optimal, which is realistic protocol, we will have two types of irreversible entropy production that come because there's still coherence and there's also classical non-thermality. And these two types of irreversible entropy production will lead to a reduction of the work that can be extracted. And they will also lead to something called quantum heat. So there will be an occurrence of quantum heat. And one can show in this paper that the extracted work is equal to the maximum that you could extract minus. And then here are the two irreversible entropy production contributions that come again from these two basically having still coherence and non-thermality left. And in a picture, you can see it like this. So this is the maximum work that you could extract, and it gets depleted when you still have either coherence or non-thermality before you couple the system to the bath. So this is important, of course, for any experimental realization, because you will never do the perfect protocol. So you will still get positive extracted work, as you can see, for some variation here. The yellow plane indicates where it's zero. So basically, once you hit that plane, you can't extract work anymore. Then it becomes negative. So in other words, you have to pay work to do the process. But as you can see, even if there's a little bit of coherence left and some quantum irreversibility, you still get some work out of the process. Okay, let me move on. This now links a little bit to this quantum correlation part that I touched on already. So we can also think about coherence work with side information. So what is side information? Side information refers to when you have the system correlated with some auxiliary system. And that was analyzed by Rio et al. In 2011. And what they showed is that, okay, let's start with the standard Landau erasure. We are already familiar with this. The Landau erasure says that when you move your state rho to a pure state 0, you will have a heat generated that's proportional to this. And that also corresponds to a work cost. So in other words, you have to do work to do erasure. And this energy is converted into heat after all. What they showed is that when you do Landau erasure with side information, you get a different answer. So this is a state rho SA of the system and an ancilla. And this state can be correlated, classically correlated, or entangled. If we just look at the reduced states of this global state, rho S and rho A are the reduced states. What we can do is we can think of a process where we take the entire rho SA state and move it to a state where we have on the system side the 0 state left. So in other words, it's just like this situation. So on the system side, we've done erasure, and on the environment, on the ancilla side, we've done nothing. So we choose our final state rho A to be exactly the same as the original reduced state of A. So on the ancilla side, nothing has happened. On the system side, erasure has happened, but we've done this here in a global setting. So acting on the entire system and ancilla. And what Del Rio et al. Showed is that you can extract work smaller or equal to minus kBT, and here is S is the conditional entropy of the system and the ancilla in the global state. So what's important here is that the bound is achievable. So it actually means that you can have an extractable work that is minus kBT times this S, okay? And it looks bad because there's a minus here. So it seems to tell you that the extractable work is negative, which means it costs you work. But the really strange thing is that you could gain work if the conditional entropy was negative, right? If this guy is negative, then you have two minuses. This becomes a positive thing, and the equality sign is also valid. So we can get a positive extractable work if the conditional entropy is negative. And one of the key things in quantum information theory is that the conditional entropy can be negative for some entangled states, rho is A. So that's amazing because it tells us that when you do Landau erasure with side information, you can actually do the same process or the same end result. Let's say if you just look at the system side and you don't pay work, you get work out. So there is another quantum difference basically to the whole story. Now, what we wanted to do in our paper back then was to take the same logic. So we want to do coherence work extraction. We already discussed this, right? But now we want to do it with side information. So again, it's exactly the same story, but instead of doing Landau erasure, we want to move rho S to eta S. So the S here stands for system, while the rho A and rho A are the ancilla states that is not supposed to change. And what we find is that the coherence work that one can extract now with side information is firstly the same as before, that's this term, plus something that goes kBT times delta, and delta is a positive measure of correlations. So in other words, again, with side information, we can get more work out than if we didn't use the side information. If you're interested in what exactly this delta is, basically you will have to look at the paper. Here's a short summary. This delta is related to quantum discord, but it is not the same. So it is somewhat related. It's a measure of correlation. This relates to the question before about the states, this selective and unselective measurement. So here now we have the situation that we have a global state, rho AS. We measure the system and we measure the system again in the energy basis here, EK. And so this eta Ka is the state of the ancilla after the system was found to be in the kth energy eigenstate. Okay, this is the reduced, or this is the conditional state of the ancilla given a result of measurement on the system. And then you take the entropies of those states for different outcomes and mix them with probabilities pk. Well, basically that is then what gives you the delta. So clearly it's going to be dependent also on the basis in which you measure. Could be Hamiltonian or could be a different observable. Okay, so that's what this delta is, and it is a positive quantity, so you do get more work out with side information. Yeah, that's what this says. So more work can be extracted from a system's S coherences if one has access to an ancilla A, which is correlated to S. Locally, the coherence work extraction with side information looks exactly the same as simple coherence work extraction. So if you just look at the system, it looks exactly the same. But globally, the correlations between S and A are used up really as a resource to extract more work. Of course, the final state doesn't have correlations anymore. We've assumed here a product state. Okay. Good. Now I've hopefully sufficiently convinced you that the quantum case is much more interesting in a way than the classical case. Now I throw a spanner, namely what Chris Straczynski talked in his talk at the Quantum Thermodynamics conference basically seems to tell you the opposite. Okay, so I will not be able to give his talk. Please have a look at his talk yourself. You might also want to have a look at this paper here that he published a couple of years ago with Kwan and Rahaf. So the argument is, yeah, I'm not going to be able to explain all of this, but basically he finds something in the classical world that he identifies with what we call quantum coherences in the quantum world. And what he identifies is, he calls it inhomogeneous. So inhomogeneous classical phase-space distributions are the ones in his way of saying, are the ones that are like quantum coherences, okay? And then he asks, can we extract work from classical inhomogeneities? So that's the question, and he answers in the affirmative. So he says, work can be extracted from quantum coherences, that's what we just discussed, but also from classical inhomogeneities, okay? And so he concludes there does not appear to be an inherent quantum thermodynamic advantage. Okay, so that's slightly the opposite of what I just told you. Basically, I tried to make the point that quantum coherence gives you extra work that you couldn't get classically, but he has identified another way of understanding the same thing in a classical situation where you, of course, talk about phase-space distributions. And again, you find actually a classical analogon, which is often the case. So check out the talk. I'm very interested to see what comes out of this in the future. Good. So I see that I don't have that much time left. So I'm going to probably just very briefly mention these things. So this is now about a different aspect of thermodynamics in the nanoscale. So it could be classical or quantum. The main thing to think about now is, so it's called strong coupling thermodynamics. The main thing to think about is that when you talk about macroscopic systems, then the coupling to the environment can be neglected. I mean, the coupling is only there to thermalize a system, and that's all it does. But when thinking of smaller scale systems, the coupling to the environment becomes really so relevant that you cannot just ignore it. You have to actually take it into account for any thermodynamic analysis. So the general task in this framework here is to identify corrections to thermodynamic potentials, which we will talk a little bit about here, and also to fluctuation relations, which we won't talk about here. So we're interested in what happens when our large system becomes small and the interaction with the reservoir is actually not negligible. So the simplest way of understanding what the difference would be is in the recoupling limit. If you take a global thermal state of a system, reservoir, interaction, and you trace over the reservoir, basically you can forget about the interaction part in a recoupling limit. And what that means is that the reduced state for your system is just a Gibbs state for the system Hamiltonian itself. That's what we use in thermodynamics all the time. But for general coupling, so when the interaction is not so small in comparison to the system Hamiltonian, then when you take the trace over the reservoir, this will not be equal to the Gibbs state. Okay, you won't. But you can identify, if you wish, you can identify, define a new system Hamiltonian. It's basically just a logarithm of the state rho. And this new system Hamiltonian here is called a Hamiltonian of mean force. And by construction, it will depend on the coupling strength, V int, and also on the temperature. So this is quite a different Hamiltonian than standard Hamiltonians that you've seen in basically in undergraduate physics. Hamiltonians there never depend on temperature. This one does, so it's an effective Hamiltonian. Okay, so a lot of work on the Hamiltonian of mean force, both in the classical case and the quantum case, going back actually to Kirkwood from the 30s. So it's used a lot in chemistry, in fact. But in the sense of thermodynamics, we are seeing quite a development here in the last years. And I can point you to Harry Miller's chapter here in the book, Thermodynamics in the Quantum Regime, where he discusses the Hamiltonian of mean force a bit. And also you might want to see Philip Strasberg's quarantine thermo talk, where he discusses strong coupling thermodynamics. Okay. So I will very briefly talk about this thermodynamic energy temperature uncertainty relation, which is in this framework. So the question we had when learning about this strong coupling thing was, well, there's Bohr's energy temperature uncertainty relation, which says that whenever you have a thermal system, there's of course uncertainty in your energy. So you have a variance of energy, that's delta U. That's sort of the variance of your energy here. But there's also a variance in temperature or inverse temperature here, which we will discuss in a minute a bit more. And so you can never be completely sure of both of them at the same time. So there's a sort of uncertainty relation here. And that, yeah, that was something that Bohr said a long time ago. And of course, this the arguments that they proposed at the time, they were valid for systems weakly coupled to environment. So again, the interaction term can be neglected. And what we were interested in is, can you correct this for systems that are strongly coupled to an environment? So how does this inequality here change? Yeah, so now I have to sort of skip a few things. Maybe the main thing to say is, well, we have to be able to establish such an uncertainty. We first need to talk about energy uncertainty. And one of the things that happens here is that, let me just skip to the next slide, is that in the recoupling limit, we have a Gibbs state with respect to the Hamiltonian, the standard Hamiltonian, and also when we calculate the energy, we calculate it with respect to the standard Hamiltonian. But when we go to strong coupling, as we already saw, we get this Hamiltonian of mean force in the Gibbs expression. But when we calculate the energy, and we calculate the energy with the standard thermodynamic relation, which relates it to the partition function, then this is not the same as taking the expectation value of rho with respect to the Hamiltonian of mean force. Okay, so it's not HS star that appears here. It's a new operator, ES, that appears here. So in other words, while in the weak coupling limit, the same Hamiltonian plays the role in two places here and there. In the strong coupling limit, this equality vanishes. HS goes there. ES is actually is beta times HS, and then take the derivative with respect to beta. So you can see, of course, that if HS star was not depending on temperature, if it was not dependent on temperature, then ES would be the same as HS star. But when it does depend on temperature, there starts to be correction terms. Okay, there starts to be additional terms, so the ES will be different from HS star. Okay, so so the point is then, just to go back briefly, the point is the energy uncertainty is now going to be the variance, or the square root of the variance of the operator ES in the state rho S. So it's not HS star, it's ES. Okay, that's how we've identified delta U. Next thing we need is temperature uncertainty, delta beta. And the context in which to set this up is optimal parameter estimation. So when you consider all possible measurements on a quantum system, what is the ultimate precision that we can hope for when you try and do an estimation of a parameter? So you have your thermal system, you know it's thermal, but you do not know what temperature it has. So you do many measurements and you try to estimate your temperature. And what you find in general for such problems is something called the Cramer-Rao bound, which tells you that a parameter estimate is bounded from below by 1 over the Fisher information here. And we were able to take this for the specific case that we're discussing here for temperature, so inverse temperature. And then the Cramer-Rao bound basically becomes this. There's a few steps in the middle that I'm skipping. But basically delta beta becomes bigger than 1 over, and here we see delta U squared minus Q. So what you should take away from this is that for the moment, forget Q. If you forget Q, you have delta U squared and then a square root, so this is delta U, okay? So then you get the standard uncertainty relation back, because it tells you delta beta times delta U is bigger than 1. What is Q? Well, Q is the correction that comes when you have strong coupling to the bath. And Q is called the skew information. Q is the skew information in our case here between, it's about whether or not two things commute. And here the two things we're interested in are the energy operator ES and the state rho S, the reduced state. So these are commutators of ES and rho S to some powers and then integrated and so on. But the main thing is it's commutators. And again, remember rho S, of course, it's e to the minus beta HS star, where HS star is the Hamiltonian of mean force. And ES is not the same. So they don't necessarily commute. So for a damped harmonic oscillator, your standard example, if you take the Hamiltonian of mean force to be this, then your ES operator will be, there's a term that's proportional to HS star. So that part will commute, but there's also this term, which has annihilation and creation operators squared that don't appear in HS star. So this part will not commute. And that then gives rise to a skew information Q that we've plotted here on the right. So you see, for different coupling strength, you have different amount of Q, and it tells you the non-commutativity between your state of the system and the energy operator. Okay, so to summarize this part, generally, it is possible to include a systems coupling to environmental degrees of freedom in a generalized thermodynamic framework, and this is where I put a lot of references to a lot of works that you might want to check out if you're interested in this. In this particular situation that we discussed here, we were interested in this uncertainty relation, and what we needed here is that the energy operator ES, which includes the strong coupling corrections, and the system's equilibrium state, which is this, they will not commute, and this gives rise to skew information Q. And this is our inequality here, or our uncertainty relation. And as you can see, the uncertainty in temperature, delta beta here, is of a system is larger when its equilibrium state is not diagonal in energy. Okay, I say this again. So when 0, we get the standard Bohr uncertainty relation. So there's a sort of delta beta is at least so and so much. But if Q is non-zero, we have something positive minus Q. This is a positive thing. So it will reduce the denominator, what's on the bottom of the fraction. So it's a smaller fraction at the bottom, which makes it bigger at the top. So when Q is non-zero, the top will become bigger, which means that actually the uncertainty that we now have combines the standard thermodynamic part of the uncertainty, the sort of energy uncertainty, even instead of super classical, everything normal, no strong coupling, plus a quantum uncertainty that comes from coherences between the state and the energy operator that arise because of strong coupling. Okay, and it makes the uncertainty larger. So it's a combined uncertainty relation. Okay, so I think I'm pretty much done. So questions quickly. So it's not really that clear how to quantify exactly weak coupling. So how do you actually say whether it's weak or not? So there's a sort of operator problem here. How do you compare this? Do you take the operator norm, or should you just think about which parts of the operator are occupied in terms of their energy of their eigenstates? The dynamical part we already talked a little bit about. We haven't touched on this at all today. And then there's also experimental methods of accessing the information about systems, strong coupling, and thermodynamic correction. So at the moment, we don't have clear experiments that really show anything about strong coupling, but we should think about how to, in the future, make such experiments possible. Okay, I will actually skip this just to say there's some relation. Actually, maybe Francesco will be interested in this, or I'm interested in talking with him about this. So there's this. Well, yeah, this is about spin dynamics in a magnetic field, but one can derive also a general spin dynamics equation similar to Caldera-Leggett, but a bit different, that results in a spin dynamics equation that's fully quantum thermodynamical and recovers what is known as the Landau-Lifshitz-Gilbert equation, which is used widely in magnetism and is also used, for example, for describing hard drives that are developed in technology. So yeah, if you want to know more about this, maybe go to this talk and see that one. Okay, so I end with a brief summary of the people also who were involved in this work. So we started with this work on coherence. This was done together with Philip Kammerlander at the time. And then I also discussed about the irreversibility aspect of this. This was done together with Hamid and Alexia. And then we talked about the strong coupling case, which led us to this uncertainty relation. This was done with Harry, who's now at Manchester University. And finally, this is what I didn't really discuss, but there's also the spin dynamics equation, which also relies on coupling a system to environment, and that's on the archive here. Okay, and with this, I thank you very much for your extended attention. Thank you.
Okay, thank you very much, Jeanette, for this very interesting overview. So we have already 2 questions. So one question, I think it's in 2 parts, so I'm just trying to understand. Yeah, so maybe, so yeah, concerning the second open question, so do the works on the so-called return to equilibrium, sorry, answer this question. So I think maybe it's a bit confusing. Yeah, so I think this is related to this first question. So let me ask first the first question. Could you please repeat in which instance the work is extracted? So I think it's related to the, yeah, when you choose the work extraction from coherence.
Okay, I'm not 100% sure. Is it this with side information or without?
Yeah, maybe I can ask sorry, Anton. I can ask him to retype this question, make it a bit more precise. In the meantime, we have so another question from Nina Mejier. So for the strong coupling issue, does your result mean that when coupling is strong, but interaction Hamiltonian commutes with the HS and HB, then the uncertainty relation is not influenced? Sorry if I missed something.
Yes, I think that's correct. I would have to go through that a bit slowly, but I think that's correct. So if the interaction Hamiltonian commutes with HS, I think that the actually not so obvious. Sorry, it's I don't actually know the answer. It's a good guess. So I think the guess is if the interaction Hamiltonian is commuting with HS, then of course the entire state rho s will be still diagonal in the HS basis. Okay. But the question is, what is ES going to be? And ES is a derivative of, yes, it will not change. Yes, yeah. Because the basis is always the same now, even though ES may have prefactors that are temperature dependent, I think the basis will always be the same. And yes, in this case, Q will be 0. Yes, that's correct. But if the interaction is not commuting with HS, then this will not be the case.
Yeah, I saw also that we have people raising the hand, but now I will ask. So Ilya, I'm a bit confused how to. Oh, yeah, maybe here. No.
Okay, sorry, I'm just allowing Anton to join and ask his question. Anton can ask a question.
Yeah.
Yes, thank you very much for the very interesting talk. My question concerns the second open question concerning the dynamical convergence to equilibrium. Could you please show the, yes, this one. Do I correctly understand that the question is how to rigorously prove that the state is converged to such an equilibrium state?
Yes, absolutely. Yes.
My question is that there are some rigorous mathematical results of this kind.
Yes, there are. You're right. Yes.
Called return to equilibrium. So do these answers sufficient, or are they not detailed enough?
Yeah, Anton, I thank you very much for this question. I would very much be interested in any papers, you know, that do that in general terms. What I am aware of is, so again, I have quite a few papers shown up even in the list for this Hamiltonian of mean force. I'm aware of papers that show for quantum Brownian motion that it is always the case, that you get a dynamical convergence of the local state to, so basically, this, just for the others as well, this is about when you set up your system originally in some state, okay, and then you couple it to the environment, and then you run the evolution time long, you go to the steady state, will it be equal to this reduced state of the global thermal state? That's the question. And that's been shown, yes, for quantum Brownian motion, for example. So specific Hamiltonians have been shown to have this property. And it's also been shown to be true if you go for a small coupling strength. So you expand to second order in the coupling strength. And for example, this paper that I show here does that. So they show what the Hamiltonian of mean force is, and they also show what the master equation does and what steady state it is, but to second order in the coupling. So in other words, this is not this super strong coupling regime where you can't expand to second order. There, I think there's still huge uncertainty. If that
to my knowledge, sorry, to my knowledge, there are general results, not only for weak coupling and for rather general Hamiltonians. Let me send such papers to you by email later. So that's yes. Very to discuss. So,
yes, very interesting. Thank you very much, Anton, for the question. Yeah, thank you.